Hi everyone. So this is a video in which I'm going to talk through limits and derivatives. I want to introduce limits as a way to motivate why we're using derivatives, and then to define derivatives and to show you how we're going to use them for physics specifically. It's not going to be very theory heavy. It's going to be mostly talking about physics concepts and application. So first of all, what's a limit? As a refresher, um, imagine that I have a function like this. So I've got some function that's x squared minus 1, and then x minus 1. So x squared minus 1 over x minus 1. If I try to evaluate this function at 1, it would be undefined because the numerator is 0 and the denominator is 0 when I plug in 1. So we need some way to figure out what the value of this function is at 1. So the way we think about this is we take the limit of this function as x goes to 1. And effectively what that is doing is it's asking what is the value of this function as you approach 1. Not when you plug in 1, but as you approach 1. And there are many different ways for evaluating limits. There's a lot of tricks. And usually we need some trick. Usually we need a trick to evaluate a limit. And some of the tricks are easier than others. In this case, you might be able to see the trick. Here, what we're going to do is we're going to expand the quadratic on the top. So this expression is equivalent to the limit as x goes to 1. If we expand the top, we get x minus 1 times x plus 1 on the top. And I'll leave it to you to confirm that, in fact, when you do FOIL that out, you get x squared minus 1. Because this is how we can do it, then we can cancel these two things. And this limit is equivalent to x, limit x going to 1 of x plus 1. And now we can, in fact, just plug in 1. And if we do that, we get 2. So the limit of that original expression, which was undefined initially the way we wrote it, is 2. And we evaluated the limit in this case by expanding that quadratic on top and canceling the root at 1. Okay, so that's a really brief refresher on limits. And so why in physics do we care about limits? Why do we care in physics? Well, here's an example. So imagine I've got, scroll down a little bit. So imagine, I'll draw a graph here. So I've got a graph. And this is a position. So I'll call this a position on the y-axis and time on the x-axis. So we're looking at a position versus time graph. And this could be for anything, but let's just say it's a butterfly. So this is the one-dimensional position versus time for a butterfly. So we're looking at the x position of a butterfly. So let's say it looks like this. It's kind of flying back and forth maybe. All right. And as a physicist, I might want to know a lot of different things about this graph. Like I might want to know what the velocity of the butterfly is at different times. And if you think about how you would approach that problem, you run into limits pretty quickly. So I could approach it this way. So let's say that I take this point here. So this happens at some time. I'll call this time t naught. And then there's like another time over here. And I'll call this t naught plus delta t, so that the time elapsed from my first and second point is delta t. Okay, I could figure out the average velocity between these two times, because by definition, The average velocity is you take the displacement covered, I'll write V average like this, is a displacement, so a change in position over a change in time. So in this case, I'm going to have to label some other variables here. So let me call this first one the initial position, and the ending the final position. So if I wanted to calculate this, then I'm doing the final position minus the initial position over the change in time, which, as I've defined it, is just delta t here. So t naught plus delta t minus t naught. So that's fine. But that doesn't really tell me the velocity at any particular time. It tells me the average velocity between two times. If I wanted to answer the question, what's the butterfly's position at a particular time? Now I'm talking about an instantaneous velocity. That is, the velocity at a moment in time. So the instantaneous velocity, that's the velocity at one moment in time. And if you think about how we could do this, so let's say we want to find the velocity at t naught. So I'll write that this way. The velocity at time equals t naught. Really what I need to do is I need to shrink delta t so that the final position and the initial position approach the same position. If you imagine taking this spot right here and moving it this way along the curve, so that the amount of time that elapses between the initial and final positions gets closer and closer to zero, then I'm getting closer and closer to the actual instantaneous velocity at this spot. So what that looks like mathematically is I'm taking a limit. If I want the instantaneous velocity at t naught, I'm taking the limit as delta t goes to zero of the average velocity. So that's the final position minus the initial position over delta t in the limit. And this kind of looks the same as the expression before, but it's different in one really important way, which is obscured by my notation here. So I'm using final position and initial position, but I'm going to change my notation slightly. So I'm going to change my notation to say that the velocity at this moment t naught is the limit as delta t goes to zero of x evaluated at t naught plus delta t minus x evaluated at t naught, and dividing that by delta t. And so it's a little more transparent what's going on here. So as delta t gets closer and closer to zero, the denominator gets closer and closer to zero, but also as delta t gets closer and closer to zero, the numerator also gets closer and closer to zero because t naught plus delta t is getting closer and closer to t naught. So the difference between x evaluated at those two times is getting closer and closer to zero as well. So now we're in a limit which we cannot directly evaluate, and we've got to use some trick to evaluate it. What I want to point out here is that this thing that I just wrote down, this expression, which I'm going to box it in a different color to highlight it. This is the definition of a derivative. This expression shows the definition of a derivative. The definition of a derivative. That is, a derivative is what happens when you take the average slope of a function in the limit that you're going over no time or no x variable. And you can do this for anything. The reason why I'm using position and time is because that's the context we'll often see it for physics, particularly here at the beginning of the year. But really this is generalizable to any function. And what you're really doing is you're calculating the slope of a function at a single point of that function. That's what you're really doing with a derivative. So in this case, we're talking about a position function, and finding velocity of that position function by taking a derivative with respect to time. That's what we're doing. And that we'll use that language more and more so you get used to it. So let me do an example of how this actually works out in practice. So let's try it. So let's say I have a function. It's just kind of an arbitrary function. So let's say my position function is something that I make up. So let's say it's 4t squared plus 2. So what that looks like, if I were to graph it, that's going to look something like, it's not going to be a perfect graph, but it's going to be okay. So it's going to look, it's going to start not at 0, and it's going to kind of curve monotonically upwards like that. My lines aren't that great, but it's okay. You kind of get the picture. That's kind of what our graph looks like. Let's say I wanted to know the instantaneous velocity when t equals 1. So let me make some markers here. So let's say that's 1, 2, 3, 4. So 1, 2, 3, 4. And what I want to know is what's the instantaneous velocity at this point, t equals 1. So that's my question. What is the velocity when time is 1? This is a question of taking a derivative, or equivalently sort of taking the limit of the slope at that point. So what we need to do is we need to use this expression up here that we came up with for velocity. So what we're saying is the velocity when time equals 1 is equal to the limit as delta t goes to 0 of the position, just a little bit more than 1, minus the position at 1, divided by that little bit of time. This is a limit. Again, we can't directly evaluate it, but we do have a function to work with now that we can plug in. So for example, this thing right here, this is just something that, we have a function we can plug 1 plus delta t into. And for this, we have a function that we can plug 1 into. And let's see what we get. I'm actually going to do this in general first. So I'm going to be, to highlight something. So I'm going to use t naught for 1 and do it with variables first and then plug in at the end for a numerical answer. So if we want the velocity at time equals 1, we're taking a limit as delta t goes to 0. X of 1 plus delta t is 4 times t naught plus delta t squared plus 2. And then minus x evaluated at t naught is 4 t naught squared plus 2. And then divided by delta t. Like the limit I started this video with, the trick we're going to use here is we're kind of going to expand it outwards. The trick in reverse, I guess. We're going to expand this outwards and see what happens. It's going to get kind of big, but it will then get small after that. So on the top, if I expand out terms, I've got 4 t naught squared plus 8 t naught delta t plus 4 delta t squared plus 2 minus 4 t naught squared minus delta 2. That's everything on top over delta t. And you'll see here that some terms will cancel. So the 4 t naught squared cancels, the 2 cancels, and there's only 2 terms left on top. So scroll down a little bit. So if we cancel that stuff, we're left with something that looks a little bit neater. So we still got that limit. We're still thinking about taking a limit and trying to figure out how we're going to plug in 0 to delta t, which we can't yet. On top, we've got t naught delta t plus 4 delta t squared over delta t. But now we can just cancel out the delta t from the bottom. and we lose one factor of the delta t's on top. And then this expression is now something that actually we can evaluate. So we just have 8 t naught plus 4 delta t. And we can just plug in 0 for delta t now. If we do that, then that second term goes away, and all we're left with is 8 t naught. So t naught is 1 here. So the velocity when time equals 1 equals 8. That's it. And I didn't give any units, but that's probably, you know, meters per second or centimeters per second or something like that. So that's our answer here. One thing I'll point out to go backwards one step. So the original problem was about this specific time, but up until the last step where I boxed the answer here in red, there was nothing specific about time equals 1 here. So this right here, that 8 t naught, that's a general expression for the velocity of our butterfly as a function of time. So this will tell us for any arbitrary time what the velocity is. And that's really, really powerful. We didn't have to use time equals 1 exactly. We could have plugged in time equals 2 or 3 or whatever value for time we wanted here. So I'll make a special note of that. So what this means is that the velocity function, v as a function of t, is equal to 8 times t. Our position function was, as a reminder, 4t squared plus 2, and the velocity is now 8t. So this is what we would call the derivative. V is the derivative of x, is a way to say it. There's, you know, we have this relationship between position and velocity. Velocity is the derivative of position. Mathematically, that is the relationship between those two quantities. So we can always take the derivative of a position function to get to velocity. And then if we want to know the velocity at a particular time, we're just plugging in the velocity. This is great, but it would be kind of a bummer if you had to go through this process every single time you took a derivative. And I'm not going to show you the derivation, but if I have any function of the form I'm about to write, and you can prove this to yourself if you want, it's kind of a cool proof to go through. If I have a position function of the form constant times time to the constant, so a and n constants, tr variable, and I take the derivative of position with respect to time, that derivative will always be a times n t to the n minus 1. This is always true. So this is a rule. This is called like the power law rule. Power law rule, or the power rule for derivatives. Obviously, not all functions can be put in this form. This is very specific to functions of the type I've just written down for derivatives. But this is really important. You should know it. And we'll have some time to practice this as we go forward, so you can get used to it and memorize it. Eventually, you'll work with it so much that you'll just memorize it. But you can see how it works in this specific case. So we have in our function was 4t squared plus 2. So this is actually, it points to another property that I'll point out in a sec. But if I had 4 times t squared, then for that particular piece, a was 4 and n was 2. So the derivative better be a times n, which is 4 times 2. So that's 8 out front. And the new exponent of our function is n minus 1. N was 2, so we have t to the 1 here. So that checks out. The second piece, there's a second piece to the function. And for this piece of the function, a is 2, but we really have t to the 0 here. And anytime, this is an interesting caveat or exception here. If you have a constant piece that you're taking a derivative of, you always get 0. And we can think about what that means. So we should actually make a caveat here. This applies for n not equal to 0. And in the case where n equals 0, the constant term just disappears. And you can think about, if you work through the derivation, you can think about how to treat that case if you're working through the derivation. And I'd be happy to work through that with any of you. I think I'm going to leave it here for now. I think the video is already getting kind of long. Please ask questions as you have them. We'll spend some time working through more example problems, and good luck. And I'll see you soon. Bye.